One, we are using this book for the mechanics for our A levels. Okay, so I'm on to exercise 4A, question number 2. In my previous video, I explained the concept of the limiting friction, and now we shall solve some questions to see that how do we actually use those formulas to solve these problems on friction. The second question says a box of mass 14 kg is at rest. Now let's suppose this is the box. Its mass is 14 kg. Now guys, when the mass is 14 kg, so that means I should show its weight down here, which is going to be 140 newtons. Okay, W equal to mg. Okay, so when I'm showing this weight, so I should be resolving this weight parallel and perpendicular to this surface over here. Okay, so this and this, if this is 15 degrees, so this is going to be 15 degrees as well. Okay, now this component of weight parallel to this surface is 140 sine 15. Okay, and this weight perpendicular to the surface component of weight, there is going to be 140 cos 15, and here is the R. So you can see that R right now is going to be 140 cos 15. Okay, now let's see what's next. It says, then he says, okay, when there is no external force acting on the box, find the size and direction of the force of friction. Guys, there is no force which is actually trying to pull or push this box on this inclined surface. So it's now asking that what is the amount of that frictional force acting on this block. So you see that we can see that this weight of the block would be pushing this downwards, down the slope. Okay, so which force is actually stopping this right now? Yes, yeah, that is the frictional force which would be acting in this way. Let me denote it as X. Okay, so there is an upward force which is going to act against the direction of this component of weight which is parallel to this inclined surface. So that means right now the frictional force acting on this block is equal to, so this that is equal to 140 sine 15. Okay, so that is our answer to the first part. So he was saying that if there is apparently no force acting on it, then how much frictional force is in action in that case. So we have calculated that that is going to be 140 sine 15. Okay, now moving ahead, in the second part, B part, it says when it is pulled up the slope by a force of 50 Newton parallel to the line of the greatest. Okay, now he has changed the situation in the second part. Now he says that there is a force of 50 newtons parallel to this the slope pushing this upwards. Okay, then what happens? As shown this, find the size and direction of the force of friction. Okay, now this is 50 newtons. Now we have to determine that in which direction and how much is the frictional force right now. Now we must be knowing the value of this 140 sine 15 right now. Let me calculate that. 140 sine 15. Yeah, and that is going to be yeah, this is 36.2. Oh yes, now this component of weight which is 140 sine 15, that is 36.2. so what do you think, where is greater force? Is that up the plane or down the plane right now? So that is up the plane, obviously 50 Newton. So why this is not moving, this block? So now the greater force is acting upward, so the frictional force would be down the slope. Okay, and that would be this if I again represent this X, so it is not moving, so we can say that X plus 140 sine 15, that is equal to 50. So that is how you get that x equal to this is 50 minus the answer. So that is going to be 13.8. So that means at this moment the frictional force is 13.8 newtons and it is acting down the plane. Okay, and then it says okay, now the next C part, when the box is dragged down the slope by a force of 20 Newton and 10 degrees above the line of this, find the size of the... Okay, now the third case. Now he is saying that there is a force of 20 Newton which is dragging this down the plane, but that force is inclined at 10 degrees. So if I just draw this, and here this is that 10 degrees over here. Okay, so now we have to tell that how much is the frictional force. Now it is still at rest. Okay, if I resolve this 10 degrees by this 20 Newton, so you see that this is going to be, this component over here is going to be 20 cos 10, and this component is going to be 20 sine 10. Okay, so you see that these two forces, one it's the component of the weight, the other is the horizontal component of this 20 Newton, they are both acting downwards. So this means this time the frictional force is acting upwards. You see, as I gave the example of the book in the previous video, that if this will not move until the applied forces they exceed that limiting friction, and we cannot calculate that limiting friction until and unless we have the mu over here. So he's not giving us mu, so we are just not interested in that limiting friction. So now this x will be, which is going to be up this up the plane, that would be, one is 140 sine 15 plus the other is going to be 20 cos 10. Okay, so this much you can use your calculators to find the frictional force over here. Okay, now the last part, when it is pulled up by a force of this, find the size of direction. Okay, you can do the last part yourself. In the last part it says that now we are pulling this up at an angle of 15 degrees and the force is 35 newtons up here. So obviously you will resolve this and then you will see that which force is more, this one or this component, and then you can determine in which direction the frictional force would be. Okay students, we move to the fifth question now. In the fifth question we're given a can of 0.5 kg, the mass is 0.5 kg and there is the coefficient of friction 0.3, and is asking that find the largest horizontal force that can be exerted on the tin before the tin starts to move. So that means indirectly is asking for the limiting friction. The largest force that can be applied before it can move is obviously that would be equal to the limiting friction. So first of all we start by showing the weight, which is going to be 5 Newton. Okay, and here is going to be R. So we are going to calculate its frictional force through the formula F equal to mu R. So mu is 0.3 and R is 5. So that is 1.5 Newton. Okay, so if you are going to apply a force, like you push this with a force which is not more than 1.5 Newton, so this can will not move. Okay, so if you exceed your force, applied force from this 1.5, which is the limiting friction, then this can will start moving. Okay guys, now let's go on to the ninth question now. Okay. In the ninth question, we are given that a sledge of mass 200 kg is being pulled by a woman along rough horizontal ground. She exerts a force of 500 Newton at 18 degrees above the horizontal, and the sledge is on the point of slipping. Oh, you must underline first of all the rough surface and then point of slipping. So what does it mean when we say that this is on the point of slipping? Yeah, this is in a state of limiting equilibrium, and the limiting friction is in action there. Okay, so now let's show the weight first of all. The weight is going to be 2000 newtons. Okay, and the woman is pulling this, like, making this angle with the horizontal. So like before I resolve this, I should show R over here. Okay, this is R. Now this one is being resolved like this is 500 cos 18, and this is 500 sine 18. Now this is a very different question this time, because now determining R is not that simple. Like in the previous question, we just had R equal to this 2000, but here there is another upward force. So when you find this R, that R would now be this R plus this 500 sine 18, that would be equal to 2000. Okay, so we can keep this R as 2000 minus 500 sine 18. Okay, and we have to find the coefficient of friction. Okay, so what do you think that what is the frictional component right now? So we are pulling, the woman is pulling it to this side, so the frictional force would be here, that F is, I normally denote this with X, so I'm just using F for this, for the friction. Okay, so F is going to be equal to 500 cos 18. Okay, so this is 500 cos 18. So since it's a case of the limiting equilibrium, so we can use the formula F equal to mu R over here. So this mu would be F over R. So you use this exact value and this value and write your mu correct to 3 significant figures. That is the required value of mu. So okay guys, then I'll be coming with the next video inshallah, where we shall talk about the acceleration. In all these questions of this 4a, we are just learning how to find the limiting friction, how to find R, and how to use F equal to mu R. And now this would be extended into the cases where we shall be using the formula F equal to ma, where F is going to be the resultant of the forces. Okay, so now let's meet in our next video for the cases where the objects would be accelerating. Okay, goodbye.